Here we go. Talk about reflection. So, what I have here is a laser. Okay, it's up on the board. When it hits this mirror, and I'm standing over here, where is it going to reflect? Look there. You get it right? Okay. Does everybody see it? Okay. If I stand here, if I'm over here, where is it going to reflect? Ready? Everybody good? Okay. So, what this is demonstrating is the law of reflection. Okay. And this is known as the ray that comes in is known as the incident ray, and the ray that bounces off is known as the reflected ray. And the angle of incidence is going to equal the angle of reflection. This is the law of reflection. Okay, the angle of incidence is equal to the angle of reflection. Okay. Now, here's a really important detail. And this is true for all angles for this chapter. We will measure all angles from the normal line. You remember the normal force last semester? How do we always draw a normal force? A lot of times up, but more specifically, always perpendicular to the surface. Good with that? So the normal line is always going to be perpendicular to the surface. We're measuring the angle from that normal line, not from here. Not from the surface, but from the normal line. So the angle of reflection is equal, or the angle of incidence is equal to the angle of reflection. Good with that? Okay. So everybody see this laser on the ceiling? I can see it too. So can everybody else in this room. Okay, notice how we call that the law of reflection? It's not like the suggestion of reflection or like the theory of reflection. It's like the law. Like that's kind of a weightier thing. Like this always happens. So how is it that everybody in this room can see this laser dot if the law of reflection is still holding true? Does that make sense? Like it's coming this way, it's bouncing into my eye, it's bouncing into your eye and everybody else's eye. That does not seem to demonstrate that. How is that possible? And it is a law. The ceiling's pretty rough. So when it hits, it does obey the law of reflection. So the laser's coming in the blue, but when it hits, the surface is rough. And so here it obeys the law of reflection going one way into somebody's eyes. Here it obeys the law of reflection going into somebody else's eye. Here, this is known as a diffused reflection. Good with that? Say it again. Not microscopically. Right. So you see the laser pointer. When I hit this mirror, watch what happens on the board. Why did it get dimmer? It's smoother. But is it perfectly smooth? How do you know? Because you can still see it. Okay. How do you think this reflected dot, reflected beam compares in terms of the brightness? Dimmer or as strong? I mean, it's not going to be stronger than the incident ray. The fact that you can see it means it's dispersing somewhat on the mirror. So it's going to be dimmer because some of that intensity is going to your eyes and not to the ceiling. Does that make sense? Okay. So if this is a perfectly smooth mirror, what would you see on the mirror? There we go. Nothing. Just not getting to your eye. Okay. So, question. Does the laser light exist in this space here? Follow-up question, similar question. Does sunlight exist in outer space? Can you even see that? Oh, you can. That's so cool. Okay. So why can you see it now? It's reflecting off of something. If you throw the moon somewhere in space, can you see the moon? What about some planets? Why can you see the planets? Because there's sunlight out there and it's reflecting off of it. You just can't see sunlight in space because there's nothing to reflect off of it. Good with that? Okay. So lasers, someone brought this up first hour. I just thought it was cool. So the shorter the wavelength, the more apt you will be able to see a laser if you're looking down it. So like, don't look into it, but you can see as you look like along the beam, you can see it. Does that make sense? You guys good with that? I'm gonna Nerf gun you. Okay, can you see it? Yeah, dust and some fog that I sprayed. But yeah, dust. You know how like sometimes in the sunlight when it's like uh, afternoon, sun comes through the window and you see all the dust flying around. That's same effect. Actually, all right, Jacob. Here you go. Good. All right. All right. Here come the lights. So, may I remind you that your eyeball is not the emitter of light, bless you, but the catcher of light. It's the receiver. Okay. You are not like Superman or Cyclops, like laser beams coming out of your eyes. Okay. It's the recipient. Okay. The catcher of light. So, if you're looking in a plane mirror, light's coming off the smiley face, obeying the law of reflection, and going into your eye. Good with that? So you think you see this smiley face right there. This would be the object, and this would be the image. Good with that? Okay. Have you ever stuck a mirror in front of like a baby or a cat or dog or bird? And it's like looking at its reflection. It's like, whoa, it's another one of me, but it doesn't know it's like, okay. So turns out that however far the object is away from the mirror, that's how far away the image is from the mirror. Okay. So this is known as um, the object distance. And this is known as the image distance. Those two are equal to each other in a plane mirror. So plane meaning like not vanilla plane, but like two-dimensional plane. Okay, so in a plane mirror, your image distance is equal to your object distance. So as you get closer to the mirror, your image gets closer to the mirror. Cool with that? I'm going to show a reflection. You're just not going to see it. Okay. So, can you guys see yourselves? Is it good? Good angle, bad angle? Dude, right there? Right there. All right. Camden, can you see yourself? Lucas, can you see yourself? Can you see Camden? Camden, can you see Lucas? Okay. So, sounds creepy, but if you can see someone in the mirror, they can see you. Okay, so light coming from this side is bouncing off, going over to this side. Light from this side is going off, bouncing off here, and going to the other side. Good with that? So when truckers sometimes, like on trucks, sometimes there'll be a sign that says, make sure you can see my face in the mirror. Why would they say that? Right. If you can't see their face, they can't see you, and you're in their blind spot. That makes sense? Okay. All right. What height? What do you think the minimum length of mirror you need to see your entire body? Everybody have a guess? All right, I need 2 volunteers. 1, 2. You guys mind being recorded? Okay. Not many people.
We'll be on YouTube though.
You will be on YouTube. Who wants to see themselves? Who wants to hold the mirror?
Oh yeah, I can look at myself.
All right, so you're gonna hold it up. Try to hold it like vertically, like that. All right, Josie, can you see the top of your head?
I can see the top of my head.
Okay, lower it down until your top.
Lower, just to the top of it.
Yep.
A little more up, just like a tiny bit. There you
go. Okay, we're gonna hold that a little bit like that. Good. So sometimes it's helpful to just let it dangle, but
okay.
Does that make sense?
Yeah. I got a ton of space on the top of my head. Like, lower, 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 lower. There you
go. Okay. So now what I'm going to do is I'm going to start covering up part of the mirror. Start covering up part of the mirror. You tell me when your feet just start to disappear.
Okay. And there. You're at the bottom of my shoe.
Okay. So come close.
How close?
Keep going. Can you still see your shoe?
Uh-huh.
Top of your head?
Uh-huh.
Okay. Back up, like far. So Maggie, you might have to.
I need to angle this way.
Like, there you go. Yep.
I can still see all of my shoe plus the floor.
Okay. So, come close so we can compare this to your height. Keep going, keep going. So right here, about half her height. And that's irregardless, thank you, thank you. That is irregardless of how close or far you are away. Okay. Why is that? So light's coming off the top of your head, bouncing into your eye. There's not much angle there. From your foot, it's coming, bouncing, obeying the law of reflection into your eye. So you only need that much of the mirror. Okay? So most people are like, yeah, but what about when you get close? So when you're close, their head, most people are okay with the head. Your feet, check this out, still obeys the law of reflection. Gets to your eye. Okay? Here's a quick little exercise. Ethan, ready? Nice. Good stuff. All right, so what I want you to do, I want you to close one eye and look at your reflection. Okay? And take an inventory of how much of your face is in the reflection, is in the mirror. Like from ear to ear, from eyebrow to ear, to like figure out how much of your face is in the mirror. Okay? Now move the mirror close to you. Did that change? Move it at arm's length. Did that change? Oh, we can do some crazy stuff with this. So if you're looking at your own reflection, you won't see any more or less, regardless of how far you are away. Okay. What does change though is your field of view behind the mirror, behind you. Okay. So if you have it up here, I can see half the classroom. But if I have it here, all I got is one row. Does that make sense? So on your rear view mirror when you're driving, the closer you are, the more your bigger field of view. The further away, the less. That's why when kids are in the back, when you're a kid in the back seat looking at your parents, all you get is their eyeballs. But they can see all of you. Well, at least you're like torso. That makes sense? Okay. All right. I don't know if you ever realized this, but on the front of an ambulance is written that. Why would they do something goofy like that? Like that'll make like I don't know what these flashing lights mean. No, let's see. I don't even know how to pronounce that. So pretend you're driving that way, and you look in your rearview mirror, and all of a sudden you say, "Oh my goodness, it's a ambulance!" Even if you're listening to your music really loud and you can't hear the sirens. Okay, good with that. So in a plane mirror, your right and left are inverted. Have you ever played Man in the Mirror? Like, I don't know, what do you guys call it? Mirror, I don't know, mirror person? Like, mirror me. Mirror me. Be my reflection. Man, you guys have not had a childhood or something. I don't know. Okay. Some of you stink at reflections. Okay. So as I'm raising my right hand, what are you raising? you're raising your left hand. Right and left are flipped. Good with that? Okay. Popular question are like, what about the two-way mirrors or like one-way window? So this is where one side sees a window, the other side sees a mirror. This is a semi-reflective surface. The side that sees the mirror is the side that has more light in it. It's brighter. The side that sees the window is the one that's darker. So in this interrogation room, this side is really bright. This side is intentionally lights off. But if you were to turn these lights off and turn the lights in the interrogation or in the spying room on, it'd be flip-flopped. Good with that? Okay. This is also how aviator glasses work, sunglasses. Like, where do you think it's going to be brighter? Right by your eyeball or outside? Hopefully outside. Like, that's why you're wearing sunglasses, because it's bright. Good with that? Okay. Here's a fun little activity. You need a buddy with this because you need two mirrors. I remember as a kid, I remember this in the grocery stores where they take the two mirrors and like make an infinite, like it looks like there's like infinite gallons of milk. Or like, wow, look at all that bacon. Like, you know what I'm talking about? Like, okay, so get with a buddy and see if you can make that happen. You can just do this on the camera. That's cool. Notice how the right and left are being flipped. I'm on one side and then I'm on the other. That is pretty cool. I'm gonna have some fun with you guys here. Where are you? Ooh, that was bad. Anyway. All right. Okay, next challenge. Make a periscope. What's a periscope? It is like the scope on a submarine, like scope up, like whoop, so you can see over things. So if I'm like hiding under my desk, I can see over with my periscope. It takes two mirrors. How are you gonna make a periscope?
A what? Wait, what are we talking about? Yeah.
accused me of.
Oh yeah. So this that's to make it clear. I see right. I got it. Wait, you can keep right. I see right. I see right here. Wait, so Brayden, hold up, and then we're good. Okay. It's hard to figure out because everyone's like two, but oh well, it's three. That's cool. Oh yeah, I can see Brayden. Yeah, I can see you have to get this into that one. Oh whoa, I can see that. Now I can see. Oh my.
Do you see Mr. Smiley?
All right. So you figured it out. So you're doing something like this. There we go. This. Okay. Now, do you understand the path that light is taking? Remember that your eyes are not the emitter, but the receiver of light. In order for you to see something, light's going into your eyes, not out of your eyes. Do you understand? Does that make sense? The path that light is taking to see over whatever object I'm periscoping. There we go with like coming in, bouncing off into the eyes. Good? Okay. If you could, pass up those mirrors. So what do you guys think about that rule of no cell phones?
Kind of they're like made cell phones.
Next year? It's not gonna work.
I see we read it. What if you were reading it? No, we were reading it. What if
Are they actually doing it?
we were reading it?
It's a state law.
Oh, really?
I bet they already have. No, I reread it was saying something.
Some of you will benefit greatly. Okay. All right. So these are what we've been talking about are plane mirrors, like two-dimensional. But you can also have things that are not two-dimensional, not plane. So the most basic geometric shape would be a spherical mirror. So it's like you have a sphere, and then you take like a Fruit Ninja, and like, okay. So the interior one would be a concave, and the one that's on the outside would be a convex mirror. The way I remember the two, concave, you're going into a cave. Convex, it's like you're flexing, you get a bulge. That's how I put it in my brain. Okay, good with that? So a concave, you don't need to know that. We're not going to worry about that. Concave mirror takes rays, and when it hits, it reflects it to a focal point. That making sense? Right here. Parallel light rays is reflected towards from. Just towards. Okay. So some examples of that would be like a radar dish. And you know, you don't see these very often anymore. Back in the day when I was growing up, if you had cable, you'd have one of these, not that big, but you'd have a big, substantial, like 6 feet in diameter radar dish in your backyard. Now it's kind of just like these little platter sized cafeteria tray curvy things. Okay? But they're catching signals and bouncing them to this point here. Good with that? This is an attempt to produce electricity in an environmental way. It works, just not cost effective. So they have plane mirrors that would rotate with the sun and reflect all those rays to the center point here, where they would heat up water, boil it, that steam they'd use to turn a turbine. It works. It just takes a whole lot more money to make than it's what it produces. Cool with that? All right. So
I don't think the one
Have any saddle mirrors?
I don't know what those are.
It's a mix of contact.
It's like
Like a saddle point, like in geometry, saddle point. All right, so if you look at the concave side, okay, and look at it and hold it at arm's length, how would you describe your image? Upside down. So upside down, we say, is inverted. Shorter way of saying upside down. Okay? And is your image bigger or smaller than you? Smaller. So we say it is shrunken. I don't know how this is going to work for you guys, but yep, you see a nice reflection of the camera. Upside down. Smaller. All right. Now, bring the mirror close. Close, 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 close. At some point, the image goes blah, 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 like swirls. That's at the focal point. And then keep going until you get another image. You might be touching your nose. Okay, how would you describe that image? So you are like you're nearer than the focal point. Is it upright or inverted? Upright. Is the image bigger or smaller than the object you're looking at? Bigger. So it's enlarged. Good with that? Okay. Where have you ever had seen Is it a makeup mirror? Is that what they call it? Like it's two sides. One side's a normal mirror, plain mirror, then the other side makes it bigger. It's doing this, but it's just not as curvy as much. Okay, so you can be further away. So if you're like, yeah, I don't know how you guys do that. Anyway, that makes sense. Okay. So a convex mirror takes rays of light and reflects them as if they're going away from the focal point. So I'm skipping all this ray diagram stuff. We're not going to do this yet. Okay. So if you look at the convex side, how would you describe the image? Is it upright or inverted? Upright. And is it shrunken or enlarged? Shrunken or enlarged? Shrunken. Where have you seen convex mirrors? Parking garage. Yep, bendy mirrors at stores. Okay. A lot of times you'll see them in drugstores up in the corner, your gas stations, trying to prevent people from like coming around a blind corner and like, good with that. Your passenger mirror, side mirror on your car. Does anybody know what that saying that's printed on the bottom of the mirror says?
Oh, this mirror closer than a bit here.
Why would they say that? Because the image looks smaller. It's shrunken, so it might seem like it's further away. You good with that? But the driver's side on cars is a plane mirror. But when you get on bigger vehicles, like a van or a truck, a lot of times they'll put both. They'll put a plane mirror and also a convex mirror, so you don't have a blind spot. I would put convex on both sides on everybody, but you know. So good with that. All right, so that is the physics lesson today. Oh no, I got one more thing for you. Take it doesn't really matter, but like look through the concave and then look through it. Look through the mirror. Look through the mirror. You can look.
Oh, it is a one-way mirror.
Okay, you've just given yourself aviator glasses. That makes sense. It's dark where your eye is, and light where the lights are. Good with that? All right, if you could pass those forward. You got a worksheet due tomorrow. Thank you. Thank you. Thank you. Thank you. Thank you. Yep. Thank you. You're right. I'm working on it. Making it shorter.
Also, did you recommend this?